All right, titrations. We're first going to talk about the overall setup for the experiment. Pretty much what happens is that you have the volume of a substance that you need to evaluate. In the course of titrations, what we're really going to be evaluating is the um, concentration of an unknown. Now, in this case, you could know the identity of the substance, but not know the concentration of the substance. And you could use and perform a titration experiment to find out that concentration. So you'll have some volume of this unknown substance. And what you do is you add an indicator like phenolphthalein, which will change color when you have changed the reaction conditions or the solution conditions from being acidic to basic or vice versa. Then you set up a burette. A burette is filled up with the titrant. Now the titrant is a substance that you will know not only the identity, but you will know the concentration to a relatively high precision value. And then what you do is you add the titrant to your unknown solution. Now usually you will have maybe a stir bar here to like mix this very thoroughly. But you will start adding, your titrant into your unknown solution ever so slowly. And what's going to be happening is that your titrant is going to be, in the case of your unknown being an acid, the titrant will have to be a strong base. Or in the case of your unknown being a base, the titrant will be a strong acid. But whatever's in the burette is usually going to be the thing that has the known concentration. It doesn't necessarily have to be that way, but typically that's how it gets done. So you add the titrant dropwise until the neutralization reaction reaches completion, at which point the solution in the beaker will change from being acidic to basic or basic to acidic, depending upon what's present in the titrant and what's present in the solution. And when that happens, you will have that color change. And the color change will basically tell you the titration is over, at which point you basically close the burette. You stop adding it. And then what you do is you read up the volumes. Now, you will have to, before you even start the process, you will have to read out the initial volume in the burette, where you start. If you basically filled up the burette to the top mark, then technically the initial volume will be 0.00. And the final volume will be wherever you stop. The one thing about burettes that you have to keep in mind is that they are accurate pieces of equipment. They will read out volumes to 2 decimal places. All right, so wherever you land, you have to end up with 2 decimal places, with the second decimal place being your guess. You have to look roughly where that meniscus lies to come up with a guess as to, okay, it looks like it's maybe halfway through, so it's a little bit more than 0.5 or 0.05, or it's a little less than halfway through, so it's a little less than 0.05, etc., etc. All right, so when you get the final volume along with the initial volume, what you do is you subtract the initial volume from the final, and that tells you the amount of titrant that has been added to your solution, to your unknown solution. And then you use that to figure out the amount of unknown that you had to begin with in terms of moles. Now, this point where the color change is what we refer to as the equivalence point. This is the end of the titration because you have run out of all the reactant you started with. You neutralized it completely. All right, so in essence, the volume of the titrant added is, in essence, the volume at the equivalence point. All right, so we're going to perform a few calculations to show you the full scope of titrations. All right, so in this case, the problem will basically tell you that you have 50 mL of a hydrochloric acid solution of unknown concentration, and you titrate it with 0.5 molar sodium hydroxide. Now the volume change, V final minus V initial for sodium hydroxide is 25 mLs, right? You could be told that, or you could be told that V initial is maybe 1.00 mLs and V final is 26.00 mLs, in which case you find out the difference, which will give you the 25.00 mLs. In this example, I'm only going with 3 sig figs, but just be aware that when you read out the volumes from the burette, you're going to have 2 decimal places. All right, so what you do is you start with the reactant for which you have both the volume and the concentration. Specifically, sodium hydroxide in this case. So you have the volume, 25 mLs. You want to change that volume to liters. So divide by 1,000 mLs, which is equal to the liter. This will give you 0.0250 liters of sodium hydroxide. If you multiply this by the molarity, and the reason why you want to do that is because molarity stands for moles of solute over liters of solution. And so if you use the molarity now as a conversion factor, you can factor out, or you can cancel out the volume of the solution, right? Liters of solution will cancel out if you multiply molarity by volume in liters, and this will give you the moles of sodium hydroxide. Now, here is where the balance equation comes in. You know, you now have the moles of sodium hydroxide, so at this point you use stoichiometry. For every 1 mole of sodium hydroxide, you will react 1 mole of HCl. So that becomes the mole to mole ratio parameter of the conversion factor. So 1 mole of sodium hydroxide goes on the bottom, 1 mole of HCl goes on top. And that will cancel out hydroxide and now yield this HCl value. Now at this point, if you carry the calculation, you will end up with the moles of HCl. But what you're after is the molarity of HCl. And what you have to keep in mind is the molarity, once again, is moles over liters. Right now you have the moles of HCl. You need to divide this by the liters of HCl. And that's where the 50 mLs comes in. You have to change the 50 mLs to liters, and you have to divide it from the moles of HCl, which is what I'm going to do right here. Divide 50 by 1,000, and then divide the 0.050 liters from the moles of HCl. Moles per liter is the same thing as molarity. So when you carry this calculation forward, you should end up with 0.250 molar HCl, which should be the concentration of HCl. And so the means of performing the titration is really the procedure by which we find out the concentration of solutions for which we may not necessarily know the concentration. All right, let's do another example. This time around, calcium hydroxide is being mixed with chloric acid, forming calcium chlorate, sorry, and water. Now here you gotta make sure to balance the equation, right? Because this is no longer going to be 1-to-1. The fact that calcium has a 2+ charge and chlorate has a 1- charge means that you're going to have different proportions. All right, but kind of like before, here we're being told that we have 100 mLs of chloric acid solution of unknown concentration. We are using 0.750 molar concentration of calcium hydroxide to titrate it, and the V final minus V initial ends up being 33.0 mLs. All right, so we start with the substance for which we have the molarity and the volume given. So the 33 mLs need to be changed to liters. So divide this by 1,000 mLs and multiply by 1 liter to get the volume in liters. Okay, so in this case, that is simply 0.0330. Another way to look at it is that you're moving the decimal place 1, 2, and 3 places to the left, right? So that's another way to do it. You don't necessarily need to write out this entire set of fractions. I'm just showing you that so that you are aware of what's happening. All right, now once you have the volume in liters, you will multiply by the corresponding molarity, in this case 0.750. One mistake that sometimes people do is that they'll start, they'll look at the volume of chloric acid and they'll multiply by the molarity of hydroxide, and it's like, why are you doing that? The volume of chloric acid doesn't have to do with the molarity of hydroxide, right? So just make sure you're multiplying the corresponding volume by the corresponding molarity. So 0.033 liters need to be multiplied by 0.750 molar, and that's because that's the same thing as moles per liter. So your liters will cancel out, and now you have moles of calcium hydroxide. And here, balancing the equation is very important because, as you have noticed, this is not a 1-to-1 reaction. So even though we will have the 1 mole of calcium hydroxide on the bottom, because you only have 1 mole of calcium hydroxide on the equation, on top you have to have 2 moles of chloric acid. Okay, so this changes the picture a little bit. All right, moles of calcium hydroxide cancel out. Now you have moles of chloric acid. And now that we have the moles of chloric acid, we want to divide them by the volume of chloric acid. So divide the 100 mLs by 1,000, which will give you 0.1 liters. And then divide the moles of chloric acid by the volume of chloric acid. And this will automatically give you the molarity of chloric acid, 0.495 molar. All right, so that was the discussion of titrations. In the next video, we're going to start talking about strong, weak acids and bases, and then we'll do a few extra calculations involving the pH. So see you then.